see my screen well, right? As well? Yes. So, so we start? Yeah? Ready? Okay. We have a typo in there. Electronics. What? Okay, so this week, as you know, again, it's about electronics production. This content that we're going to see today is, let's say, trying to advance into some of the things that we'll see in the upcoming weeks for electronics programming and electronics design. And the idea is that we start getting familiar and leveling up a little bit so that you feel comfortable by when the time comes to see these things, so that you're not like afraid and super rushed into all the content that we will have. Okay. The class for today is going to be, I put it in the chat, electronics production, the second link. What is a microcontroller? And then you will see as well that the ecosystem of microcontrollers in the academy has grown a little bit. We have some few families that do different things. And today we're going to see a little bit what those families are and get to know some names, some methods to interact with them, and what are the features. Okay. So starting in the first one with what is a microcontroller. If you want to follow through the documentation, please feel free to go there. Otherwise, you can just look at my screen. So what we're going to talk about mainly is microcontrollers. Microcontrollers are these little tiny computers on chip that can do very smart things. Okay. Let me show you. So if you look at the camera, what we're looking at and what we're going to see today mainly is this guy here. This is one microcontroller, or this other guy here, or this is the same. Actually, okay. Let me upgrade my system. I should change it to that one, I guess. Logitech. Wow. Okay, so repeating again. You see that I have 3 Arduino Unos in my hand. And in total, they have 5 microcontrollers in 3 boards. This first here has a microcontroller. You see it in there in the camera. That is a single microcontroller that is able to interface with all the functionalities that we need in the board. This other board has 2 microcontrollers because this little one in here doesn't have the, for instance, the USB functionality. It doesn't know how to talk USB, so we need another one that is able to do that. And this other here, even if it's a much larger microcontroller over here, is actually the same, and it also needs a small microcontroller in the middle that is able to talk USB. So you see that even if I have 2 Arduino Unos, I have 3 different setups, 3 different microcontrollers, and not all of them, the main brain of the board that we're going to design is able to cope with all the things that we need to do. Okay? So the first thing to understand is that microcontrollers are, if you can pass them, you can see a little bit, are small computers in integrated circuits that have different functions, possibilities, depending on what the manufacturer did, and that not always we're going to have everything available inside this microcontroller to be able to do what we want in our board. Sometimes our board will have 1 microcontroller, we'll have 2, we have 3, and we will see from small setups to more complex ones, trying to make boards that can have features like, for instance, an Arduino. Here, one of the families of microcontrollers that we're going to see later is called the ATtiny. ATtiny is from a manufacturer called AVR. You probably will start seeing that name very frequently, and this is the block diagram of what functionalities that microcontroller has. You see that it has some interface. Here, normally the interfaces are called ports. So they are ways that the microcontroller can interact with the outer world, let's say. There is something called registers that we will see little by little. There is something called ALU, so arithmetic logic unit, which is the unit that makes numbers and it's able to calculate things. It has some different memories. It has what we call timers. The microcontrollers many of them don't know how to count time even. They're very silly. So they need somehow a reference, like an orchestra director telling them what pace to keep up with the processing. And also some other interfaces with the outer world, for instance, an ADC, which is an analog to digital converter. All these we'll have a look today. I'm gonna try to go through different functionalities and things that microcontrollers do. But just think that a microcontroller inside is like a small city that has different blocks, and each of the blocks does different things, okay? So there's no single microcontroller that has everything, and there's no unit inside a microcontroller that is able to do anything. They are split into different tasks because the way that the circuitry is implemented inside changes for efficiency and for being able to execute different tasks in different ways. So if we wanted to define a microcontroller, we would say that a microcontroller, and this is one of the first things that I'm going to ask you, is, well, what is the difference between a microcontroller and a microprocessor? Would you be able, do you know? Any idea of why?
Just computes.
Also a microcontroller.
That's just that.
That's one difference. Who does just that?
The microprocessor.
The microcontroller. The microcontroller normally are dedicated to one task. They have one thread. Let's say they only have one line of processing, and they can only do one thing. It seems to us that they can do it very fast. So they can do many things at the same time, but that's because they are doing it very fast. Normally, microcontrollers have internal speeds of around 8 megahertz, 16 megahertz, 20 megahertz, and that is 20 million times per second. So they do something in their clock is ticking, let's say 20 million times per second. And each time that clock ticks, they are able to execute something in machine code, okay, in the instructions that the microcontroller understands. So even if they only have one thread, it is, from our perspective, seamless, or it seems that they can do many things, but only because they're working very fast. Another difference is that they are very low power devices. Normally, microcontrollers operate at 5 volts, DC, of course. If you want as well, you can operate microcontrollers at 3.3, like normally. It's becoming really common. Some microcontrollers that we'll see as the silicon gets more and more efficient, they start to work at 3.3, and it gives us some problems because not all the electronics in the world are working at 3.3 volts. So we have to adapt 5 volts to 3.3. You will also see that as the silicon gets better and we are able to make it tinier, we'll also start using 1.8 volts. So it's a trend to going down. And that's because you lose less energy into transmitting things at 1.8 volts than at 5 volts. Of course, when you have, let's say, a signal that is at 1.8 volts, but you want to transmit something at 1.8 volts, since the range is very small, if you have a lot of noise or you have some noise, then your signal can get disrupted. So that's why it took some time to go from 5 volts to 3.3 and now to 1.8. But little by little, you'll see this trend in microcontrollers to go even lower because it saves energy, and that is good. let's say, for the same operations, you consume less power. Okay.
And for the microprocessor works at higher voltage.
The microprocessor, yeah, normally works at a higher voltage, depends on the unit, but it normally is either at 5 or 12 volts. And they have different units inside of them. As well, microcontrollers, microprocessors normally are just dedicated to computing things, to do tasks that require more complex operations. Microcontrollers are simple, but they have the possibility to interface with inputs and outputs. And that is very important because, as we will see during the whole Academy electronics is not just I compute something, I make numbers, or I do, let's say, 2 plus 2, is I send something from the world, I do something in my microcontroller, and then I output something. So I have a sensor, and this is one of the first concepts that we will start doing in electronics programming. I send something, I process something, I output something. If you look at that machine, I put it like that. If you look at that machine, that 3D printer, it has temperature sensors, it has end stops that are just normal switches, it has motors, and it has a board that is able to read all of that and output temperature for the nozzle, movement for the motors, temperature for the bed, and regulate all that. That a microcontroller is very good at doing because it has a lot of inputs, possibility to calculate, and then possibility to output in different levels to different actuators to do different things. Okay. Now, till here more or less. Okay. So, in microcontrollers, this is probably the one and only. We will see this theoretically, and we won't see it again. But maybe in electronics programming, but not that much. You have 3 memories, or mainly 3 types of memory. One of them is where, let's say, the program that you're executing, let's say imagine your Arduino code that has some variables and has some state variables or things that you're processing are stored. That is what we call the data memory. Is where the, let's say, the runtime of the microcontroller is happening. Is that concept of runtime familiar for you? No? So imagine this microcontroller. I'm going to program, I want to program it. I do some coding in my computer. I compile it in my computer. It means I make a small file that then I transfer in here. Once that file is in here and I give power to the microcontroller, it's going to execute whatever that script does, right? It's going to turn on one LED, do the operations of the machine, etc., etc. That is called the runtime. It means that the time at which the script is running. Okay, so it means that all those variables, imagine for a 3D printer, it would be the temperature of the nozzle, the temperature of the bed, the position of the motors, etc., are stored somewhere in the memory of the microcontroller so that you can access them. That is called data memory. In another part of the memory, you have the program memory, where you store your script, where you store your binary files. We will see how to compile them and make them in the electronics programming week. But basically, you put in your microcontroller something. That script has to be stored physically in the memory that is called program memory. All those two, one of them stays, the other one doesn't. The one that stays is the program. If you unplug the microcontroller, the memory will still be there and it won't disappear. You plug it and it does the same ever again. If you unplug it again, you don't have to reprogram the chip. But it won't remember what happened before. It's not like your computer that has a hard drive and that has some, whenever you turn on your computer, you have to create your files again, right? In these microcontrollers, whenever there is a power out, the memory, the data memory is erased. you don't recuperate it, but the program still stays there. Okay. This concept of volatile and not volatile memory, you see it also in computers, and maybe you're more familiar with the old ROM, ROM, and the RAM, RAM. So read random access memory and read-only memory. In your computer, random access memory. So it's the RAM, what you're doing in your computer. If you don't save it somewhere and you turn off your computer, when you turn it on, everything is gone. Right? You have to start over again. The same with these guys. And lastly, there's one last memory that is called EEPROM, which is a memory that is stored in non-volatile. So it stays, it has one small section that in which you can store some things. And those things normally are very small. If you think of one EEPROM, it could be around 2 kilobytes, maybe. And you cannot write endlessly in it. So if you write 10 times and erase it, the memory loses life and it starts getting like old. And you have to be careful how many times you're writing it, because at some point it won't be effective, because you are writing directly into transistors and then they lose, let's say, the possibility to store that information permanently. So you might have like 500,000 cycles of storage. If you do that repeatedly for more than that amount, then you're done. Then there's no more possibilities for you to write in the EEPROM. So three things to remember. First one is the memory that is non-volatile is the program memory. You can write things in there and you power off, you power on, it stays there. Data memory, it doesn't stay, it gets deleted. EEPROM, when you take it out, so you power off the microcontroller, it doesn't get deleted, but there's a cost. That cost is that you cannot write and erase the memory many times because it fades away and it gets old. Okay. Now, inside your microcontroller, the program memory has one area that is called the boot area or the bootloader area. And you will suffer from this area a lot in electronics. The bootloader, basically, when you start doing serious things, is the memory that is stored in your microcontroller that starts telling the board and the microcontroller to execute the main program. What does this mean? Is that imagine that you make a board, a code, sorry, that flashes one LED in this one here, in this board, okay? Only does that, just turns on and off one LED permanently, and that's it. The microcontroller inside of it needs to know when to execute that LED, like that LED function on its own. And it normally doesn't know unless there is this boot flash section of the microcontroller that basically starts running the script that you put in there. So it boots up, it's like the BIOS or BIOS or in your computer. That is the one that takes care of getting things started and then triggering the script that you put in the program section. I let you read here what the bootloader is in a more advanced way. This is not what the bootloader is. This is Edu doing his fun things. Some of the chips that we will see, like 80Tinys, they are so small. Think that they have, for instance, 8 kilobytes of memory. 8 kilobytes of memory is really little. Imagine when was the last time you saw something 8 kilobytes big? That is the memory that you can have in the microcontroller to program. Some of them, they don't have bootloader section. And in many ways, in many cases, the first time that you open the microcontroller and you start programming it, it won't be able to recognize everything. You have to load the bootloader and then start doing things. If you have Arduino, and open the tool sections of Arduino, you will see that there's one little line that says burn bootloader. Let's wait for it. Basically, you will fight with this as soon as you get started with electronics programming, because when you take one chip out of the board, out of the box, they don't normally work. You have to burn, so you have to guide the bootloader inside of it so that it starts listening to you. Think as microcontrollers as well as very silly and very dumb. They don't normally know anything. When we receive these electronics, that there's already something in them, so that we are able to run to work with them. The things that you're gonna do in here are much more low level, so you have to get the whole process started, and this is one thing. In Arduino, you'll see this is the burn bootloader instruction here, that you will see this in the future. Basically, it allows to put this first program in the Arduino or in the chip so that you can interact with it in the future by putting your scripts inside. After this, you will be able to click in here, and whatever you have in this script, send it to your Arduino. Before you do this, in many microcontrollers, you won't even be able to talk with it. It's like a brick for you. There's no communication because there's no one like an USB or a port waiting for you to talk to it. Okay, I'm sorry that this class is gonna be quite hardcore, or I don't know, many, just interrupt me if you need to, or if it's getting too heavy, okay? What else? So normally in the world of Arduino, we see that this already has, for instance, a micro USB. You are all very familiar with it already. You can connect it to your laptop, recognizes it, you send something, it works, great. Sometimes you will need other things, and this you won't have to do it this week, but it's good that you already get familiar with it, because you are going to fabricate one. What is this? These things are called ISPs, or in-circuit programmers. What they do is that they are able to talk to microcontrollers that don't know how to talk with your computer. They are like a man in the middle, a bridge that allows communication between your computer and the microcontroller to happen. Otherwise, some microcontrollers that don't have USB or that don't have a microcontroller that is able to talk USB, because many of the microcontrollers don't know how to speak USB, then you have to put one of these in the middle that is able to listen to your computer on one side and send information to the microcontroller on the other. What you're gonna manufacture this week is one wire ISP. One thing is that we say that this week is, or Edu says a lot, that is this wax on, wax off. You just have to learn how to manufacture, how to make the PCBs. But you're gonna make one PCB that is gonna be very helpful for you, the whole FA Academy, which is your own program. Why do you make that? I think it's quite important to know. And it is because all the microcontrollers that you're gonna use in the FA Academy don't interact with your computer directly. You're gonna need one of these in the middle, and you're gonna manufacture your own. Normally this costs, I don't know, 50 euros. It's proprietary hardware, and it's sold by ABR, the manufacturer of the microcontrollers. What you're gonna do here is make your own, okay? That is the purpose of the board that you're gonna do, and that you will have to keep it close so that you can use, or that you can develop the rest of the electronics for the backend, because it's the board that is gonna allow you to program all the boards that you're gonna design. So I think even if it's just to make electronics and you're just gonna take a design, produce it, solder it, and stuff, I think it's a good thing to know what you're making, and what you're making is one of these. These things, again, they are called ISPs, and of course, sorry, the world is like this, and there are many manufacturers and there are many different microcontrollers in the world. This is just for one type or one family of microcontrollers. You're gonna do another type that is called, or the, let's say the upgrade of this, and we will see later that is much simpler, but that uses what we call FTDI cable plus UPDI. We'll see this in a second, but basically it's the same thing, but an upgrade. A little bit simpler, a little bit more difficult to solder maybe, but in concept, that's the same thing. The idea, so that you know, and that I really want you to keep this in mind, what you are making this week is an instrument that allows you to program electronics that are not fancy electronics that have a lot of resources. We are not living in AVR or Atmel to make electronics that have, I don't know, 30 euro chips and things like this. You're going to start with very small microcontrollers that don't have memory, that don't have USB, and that puts you in a situation so that you learn how to program them without having the comfort of USB and all these things that these guys do. Okay, so this is it. Um, any question to here? So is it clear what these things do and what you're gonna do with this week? Okay, now we're gonna start talking about how the microcontroller starts talking to the world and what are the pins in a microcontroller. In we have the Arduino with the let me see if I can extract it. No. Well, let's see. This microcontroller here is very similar to the one that the Arduino Uno here has. Okay. You see that they have a lot of little legs. In the other format, you see that also they have some legs on the sides. Some of them, they don't have legs and they come in a format like this, in which the legs are underneath. And you solder them in a special oven, not by hand, of course, and they get attached to the PCB. And that's the way the microcontroller interacts with the PCB. What are those little legs and what do they do? We call them normally pins. Pins are the little interfaces that the microcontroller has with the outer world and that they serve for many different purposes. Some of them are just to power the microcontroller. Normally, well, as you know already, you need to give voltage reference, so ground and voltage, 5 volts. That voltage can be 5 volts, 3.3, 1.8. So you will have at least 2 pins for that. Normally, even you will have many ground pins. All the grounds in your board are going to be connected, and the same for the microcontroller. Some of the pins will be inputs. You will be able to read inputs from the outer world in a digital or an analog way. It depends. Some of the pins will be outputs, and the same. Normally, you won't have analog outputs, but you will have analog inputs. Or digital output, sorry. Why is that? Because generating a signal is much more difficult in an analog format than making it digitally. That's why, for instance, sound equipment is so expensive, because sound equipment, what it makes is it has a lot of DACs, which is digital to analog converter. Microcontrollers talk in digital, they don't talk analog. So we are able to reference things inside like ones and zeros, binary, and all these other things, but they don't talk analog inside. So making sound, which is an analog signal, is very expensive, especially if you want to make it well. So you have digital inputs, digital outputs. You have peripherals like ADCs, like to read analog signals from the outer world. Then you have some pins that are like a reset so that you can restart the microcontroller in a, let's say, hard way, not by the program, but like you put certain pins like at a central level and it does something, etc. Normally they are called ports. And in a complex microcontroller like this one that has a lot of them, let me see here. You see that they have a lot of ports. Here you see in black grounds, grounds. BDD in normally is going to be voltage. BDD is normally like input voltage, reference voltage, things like this. There's a reset already here. And the rest you see that normally are PA, PB, etc. PA and PB are normally ports. And you can guess already what is the architecture of this microcontroller by counting how many of them there are. And this is a 32 bits microcontroller because it has port A up to 31, port B up to 31. So it's only able to manage 32 ports, so 32 inputs on one side, 32 inputs on another side, and it groups them in A and B, but it has in total 64 inputs. 64 inputs is a lot of inputs to handle, and the microcontroller needs a lot of memory for that. So this is a complex microcontroller. A more simple microcontroller, we have much less. You will start with microcontrollers that have 8 inputs, some not even 6, something like this, and that you will put them inside. When you start programming, you will put them in something called registers, etc., that are like the way the microcontroller accesses the output. Just to remember is that the legs are called pins, and the pins, when they interface with the outer world, and they are not just voltage and ground, they're grouped in ports. And you will see ports of 8, 16, 32, depending on the architecture of the microcontroller. And that is something that the manufacturer decides. 8, 16, and 32, I guess that you already are familiar with that, is multiples of 2. You have that because like, you store information in the microcontroller as in binary. And in binary, you start storing like 1 byte is 8 bits. So groups of 8, 8 plus 8 plus 8 and 8. So that's why you have 8 or 16 or 32 ports possibility in the microcontroller. Do you get that actually or not? Yes or no? More or less? Right?
Yes.
Well, if you get that concept, why do we group the ports in groups of 8? If you don't have, okay, let's make a deal. It's not directed to you, it's to everyone. If you don't stop me, I'm gonna keep going more complex, and I'm gonna keep assuming that you know all these things. And if you don't ask me, I'm not gonna stop. And I'm gonna start talking about ports and architectures and bits and bytes and registers and things like this. If you don't say, what the fuck is a register? I'm not gonna stop. So if you don't know, ask. And this is like, I've been, sorry, but this is a very nice test. I've been for 34 minutes talking the same way I would talk to Victor about registers, and no one has asked a question. Come on, guys. I can't assume that you know all this, but I am assuming because right now, what I'm trying to do is like, let's see when they ask, and you haven't asked. Come on.
What is a register?
Okay. What is a register? We'll see in electronics programming, but here in this image, your microcontroller needs to know when it's running, let's say, it needs to know what the status of the microcontroller is. Let's say it needs to know how the legs of the microcontroller are. Are they on? Are they off? Are they high? Are they low? Are there 5 volts? Ground? What's the status? Am I receiving an input? Am I not? How does it know that? It reads the input and it stores that value somewhere. Where does it store it? Store it in a register. It registers the value of the pin and put it in the memory. Then you can access it or not. You might do something with it or not. But the microcontroller is keeping track all the time of how it feels. It's like I'm standing, I know I'm standing. I don't have to know, like, I'm talking to you and I go to something. I'm standing. Oh, now my leg is here. Or no, my body knows that because there's some part of my brain that is conscious about how I am. Like if this is bothering me, or if I'm standing, or if I need to think or whatever, or if I need to, but I'm not thinking constantly about that. It's a part of my brain that is storing that information. The same for the microcontroller. It's keeping some information of its status in a part of the memory that is called registers.
And when you say before introducing register, one register is the state of all the legs of all the chords, or it's one register per chord?
Good, that's a good question. So you have, let me draw. Ah. Let's see if I can draw or not. Yes, what happens? Yeah. Okay. So let me draw here. Yes. Okay. So one register is normally an array that has 1, 2, 3, 4, 5, 6, 7, 8. If the architecture of the microcontroller is 8 bits. Let's say a microcontroller can handle a certain amount of bits at the same time in its memory. It's only able to process that amount per clock, that's per unit time. So it's only able to say, I'm only able to handle 8 bits at one time. I do something with it, I put it from the memory to somewhere, I do a number, whatever, but I'm only able to do 8 bits. That's what 8 bits architectures mean. Then if you have a 32-bit architecture, if we have a 64-bit architecture like computers, then you're able to manage 64 bits at the same time. Is what it's like when you're a little kid and you say, yeah, I'm able to count till 100, or I'm able to count till 10, or I'm able to count, and very smart one says, I'm able to count till 1,000,000. These type of things. So the same for the microcontroller. It's only able to count and manage 8 bits or 16 bits or 32 bits. So the registers are going to depend on how much information the microcontroller can handle. And that is, let's say, 8 in this case. In this case, these input-output registers are each of them one pin. And this pin is a physical leg. And for instance, if it's a leg that is a digital leg, meaning that it only can be 0 or 5 volts, or low, high, false, true, binary, 0 or 1. This leg will be represented as a 0 or a 1 in that register. You have 8 legs, you have a full register. You have 16 legs, you have 2 registers. And
To register information.
exactly, exactly. So for instance, if you wanted to read in this microcontroller, that is an 8-bit microcontroller, you wanted to read 16 pins at the same time, you can't. You have to read it in 2 instructions. You're not gonna go as so low level as that. You might if you wanted, but normally you will abstract a little bit, and even the speed at which the microcontroller does it, which is 8 megahertz, is gonna be so fast for you that you're not even going to realize if it's 1 divided by 1,000,000 seconds later, which is nothing. Actually make that number. That's what we're gonna see in a second. So, just to see, this is 1, 2, 3. So each clock cycle happens at 0.000125 milliseconds. So that's really fast. Yeah. So let's imagine that the microcontroller doesn't know how time goes. It's just a piece of hardware that doesn't have the concept of time. This is something that we humans have, and that the microcontrollers need somehow someone that tells them how fast things have to go. How fast that goes, let's say how fast they can do operations, is called clock. And basically is something inside the microcontroller that tells them the time to execute instructions. Better microcontrollers or microprocessors that have 2 gigahertz, 5 gigahertz, 2.4, you see these like i5, 2.4 gigahertz, etc. That's the speed at which they can do operations. Very basic, very low level operations, but still operations. These ones are normally 8 megahertz, which means that they can do an operation, sorry, they can do 8 million operations per second. So one operation takes 1, 2, 3, that amount of seconds. So if we convert that to milliseconds, that amount of milliseconds, or to nanoseconds, so that.
And that is a characteristic of the
Microcontroller. Yes.
you can
You can, yes. If you see, let me see if I can. So, share screen. Oh, no. Overclocking. That's a different thing in computers, but it has some relationship to it, but it's not. What we're gonna do is by hardware. If you look in here, uh, if you look there, it's difficult to read. That little metal thing in there, or I'm gonna show you in a better Arduino Uno. In this image, this here is called crystal. It's a quartz crystal that when you put electricity is able to do very precise pulses. So precise that it's able to do pulses at 16 megahertz. So it's able to give you let's say like the director of the orchestra that is 1, 2, 3, 1, 2, 3, 16 million times per second. Like 1, 2, 3, 1, 2. So this is able to tell this microcontroller to go faster. And we dedicate some legs of the microcontroller to listen to that and to ignore the internal clock and listen to the clock that is giving this other unit. Yeah. Normally, well, they take different shapes. Let me see if I can find a different one. This. Arduino. So this one. No, no, no. Here, I think. No, this all has a resonator. Well, this one that I have in my hand, just sorry for the ones that are home, but it doesn't have a crystal, but it has this black box in here. That's the same. It's the same, but it's not a crystal. It's called resonator. You can use either of them. We have both in here. These normally tend to go faster. They are simpler to solder. They're a little bit cheaper, but of course, they're not as precise. It cannot be everything better, right? Because otherwise, no one will use them. So these ones are a little bit more precise. They're a little bit bigger and more expensive, but these ones are able to go a little bit faster. Okay. So the microcontroller reads things from the outside. It does operations at a certain speed, and then that speed is determined by either the internal clock, that is, let's say, its own We could assimilate it as its own biological clock of the microcontroller, or someone from the outer world that is telling it at which speed it should do operation. Of course, that operation you cannot overclock as much as you want. You couldn't put 2 GHz into this, but you can improve by maybe double or three times the normal operation. Right? So from 8 you could go out to 20, but from 8 you're gonna go up to 400. That's not normally possible. Now, let's see back in here. So the registers, I mean, we will revisit this, but are they more or less clear what they are? Okay. So we will put the information that we read from the outer world. We will read them in different pins. We will put them in registers. Don't worry about that. We'll see more into depth. Now let's understand a little bit what different types of inputs or outputs we can have.
So you didn't explain for the analogs or
That's what we're gonna get now. Yeah. So pins normally on in the microcontroller only will understand digital. Digital is this idea of binary 0 or 1. It's either high, high means normally 5 volts, or low means normally ground. True or false, 1 or 0, high or low. This is going to be, in the whole file academy, is going to be always like this. High, low, 5, ground, etc. Digital pins only work like that. They either can be high or can be low. You can set them internally to be high for something else. For instance, you turn on an LED, that means the LED is on. The pin is high. There's current going from the microcontroller to the LED and back. Or there's the pin can be input as a digital, in which case we are reading something. If I have a switch and I press it, the current is going from the outer world to the pin, let's say, and I'm reading it. Do I get a high voltage or a low voltage? That is how normally microcontrollers work, okay? In some cases, we don't want to represent only high or low. We want to represent the beauty of the world, which is analog, right? So like smooth curves, not values that are high or low, different scales of gray. And we want to represent what is an analog signal that has infinite values in the signal itself that we won't be able to represent, sadly, but that at least we can digitalize a little bit and make it seem as if it's an analog signal in a digital world, okay? What does that mean? That, for instance, the signal that we have on the top part, that is a continuous signal that has infinite values and infinite resolution, we are going to have it digitalized into this format by reading the input pins with something that is called ADC. An ADC is an analog to digital converter that basically takes a value from the other world that it has to be on the range of operation of the microcontroller, for instance, from 0 to 5, then that signal has to be 0, 5, or somewhere in between. It takes that signal and converts it into a digital representation of it. How many, can we put any signal? No, you cannot put any signal because it has to be something that your microcontroller can accept. For instance, I cannot hold more weight than I can than my own weight, or I cannot push more weight than I can my own weight, right? So the same for the microcontroller. The microcontroller won't be able to read a signal that is, for instance, 12 volts, and if the microcontroller operates from 0 to 5. Is that more or less clear? So if I'm feeding the microcontroller from 0 to 5, the signal that I'm trying to read has to be from 0 to 5. It cannot be from 0 to 12. It could be from 0 to from 0 to 3, yes. From 0 to 4, yes. From 0 to 5.5, no.
It will be determined by the sensors.
Exactly. So the sensors, the input that you'll use, the one of the first things that we'll ask you is what is the voltage at which the sensor operates? Is it compatible with your microcontroller? Is it a digital or an analog sensor? How do you talk to it? If it's an analog sensor and it operates within the range of your microcontroller, Good. Does your microcontroller have an ADC? Which means that does it have the possibility to read analog signals? It might be that it doesn't, because in this case, for instance, this microcontroller has this ADC here, but it might not be always the case. How many analog signals do you want to read? Do you want to read 10 signals? Maybe your microcontroller only has one input that can read one analog signal. So all these things you have that you will start asking these questions. We'll see them in inputs, we'll see them in outputs, but it's good that they start listening. How do you recognize these things in an Arduino Uno? If you look into the footprint of or the board, you already see here on that all these pins are represented clearly in the silk screen of the board. Here you have the power, 5 volts, ground, voltage in. Voltage in is if you wanted to get the exact same power that you are putting through here, it directs it to this pin if you want to use it for other things. But these are 5 and ground. You also have this reset here. Forget about IRF. I'll explain what that is. But here you have 2 very clear sides, analog and digital. These pins only are able to read digital inputs or output digital things. It might do very fast, and it might seem that it's an analog, but it's only digital. It can only be 0 or 5 volts, and that's it. There's no other option for that pin to be. These other ones here, you see that it's only analog in. I'm only able to read, but I'm not able to produce a signal. These analog in have ADCs behind, and they are able to convert an analog signal into a digital form. That's it. So,
silly question. I think I understand really well.
okay. So analog signal, there's no silly question. Just to be clear about it. An analog signal. Sorry, let's put it. A digital signal is only one that can be one. It can be 2 possibilities. It can be either 0 or it can be either 5 volts. It can be, if you think of the voltage levels of a microcontroller that are between ground, 0 volts, or 5 volts, it's a signal that can be either 0 or 5. It doesn't have anything in between. It's only the transitions are abrupt and they go from one state to the other. There's no 2.5, let's say. An analog signal is one that can do the rest. So it's a signal that is able to go 0, 0.1, 0.2, 5, 0.5, 0. Whatever, all the way and at however resolution you want, also however many numbers after the comma, let's say, and you want up to 5. So all the possibilities. The digital, since microcontroller only talking digital, they only can represent 0s and 5s. The inputs that we put in the analog world, let's say, they have to be converted into digital or represented internally as digital. And that's the process that we do with what we call the ADC, which is an analog to digital converter. It's the, I mean, in English, words or these things are like so magic. Like, I want to supply power to a circuit, a power supply. I want to convert an analog signal to a digital signal, analog to digital converter. It's as simple as that, you know. So yeah, it's simple as that.
For example, analog signal which is 1.3, which is the result of digital signal.
Exactly. So let's put an example. Okay, I'm gonna annotate in here. So let's imagine this signal on the side. Actually, let me do it a little bit better. Let's imagine this signal. I started really well, and then, and let's imagine that I can read this is 2.5. My microcontroller reads from 0 to 5, let's say, and this is minus 2.5. Offsetting and these things, don't worry. Let's assume that this is from 2.5 to minus 2.5, okay? My microcontroller has to, let's say, decide how this is going to be represented. And it's going to say, okay, my range is this. All this in here. Let's put it in a different color. My range is all this in here. Too patriotic. This is everything that I can do from 0 to 5. How many different possibilities do I have? Do I have 8 possibilities? Do I have 16 possibilities? Depends on my architecture, or another concept, my resolution. Do I have 16 possibilities? Okay, so I'm going to divide this in 16 chunks. Up to 16, okay? And then I'm going to say here, this one here starts, it's in between number 5 and number 6. Okay, I keep this value. This next value here is still between number 5 and number 6. I keep the same. This next value here is a little bit higher. Okay, I'll go here. The next value, the same. The next value, a little bit higher. The next value, here. The next value, the same. So I'm like saying between all the options that I can represent from 0 to 5, I split it and I say from everything that comes that is between 0 and 0.5, I'm going to put it in the first bucket. And I'm just going to represent it as 1. The second one, I'm going to represent it as 2. The third one, I'm going to represent it as 3. And everything in between, I just forget it and I put it all in the same box. And I end up with a signal that at the end, if you look at this one here, it has 1, 2, 3, 4, 5, 6, 7 possibilities.
If we understand digital like a switch that we all know,
yes,
here to represent one cycle can be 16 switches.
Exactly.
And
exactly.
then if there are only 8, we are in the middle. If they are
exactly.
we are not.
Exactly. We are getting a little bit yeah, we probably should be careful with this, but let me show you this image. Yeah. So the concept of let me clear this.
And the full register will be for the different values that we're converting. So it will be 0, 2, 0, 0, 0, 0, 1.
Exactly.
0, 0, 0, 0, 1 here.
Exactly. Exactly. So here you see, for instance, okay. Let me zoom a little. We will talk about binary and all these things a lot in electronics programming. But here, imagine that we want to represent 2 options. We need either a 1 or a 0. If we want to represent 4 options, we need 1, 0, and then 2 more. So 1, 0, 1, 1. Okay? That is 2 switches. If we want to represent 1, 2, 3, 4, 5, 6, 7, 8, 2 to the power of 8, 256 options. I have all these switches, all the combinations that I make allow me to represent 256 different numbers. In this case, for instance, what I'm doing is I take binary options and I group them in groups of 8, for instance, and I'm able to represent 256 different values in a range that it can be from 0 to 5. And I say, anytime that my input signal this is probably clear, that my input signal is at the bottom, let's say, at the minimum value that I can read is 0. If it goes a little bit higher, it's 0, 1. If it goes a little bit higher, it's 1, 0. If a little bit higher, it's 1, 1.
So that would require
That would no, this would require one pin, but two values inside your memory to read. The pin is only a single one. Well, there's two pins actually, yes. One that reads the signal and the other one that sets the reference. What the ground is, you measure always a signal between the signal itself and ground. But in this case, you represent that information internally in your microcontroller with only two switches, with two different small numbers. So from two different ones or zeros, binary options. If you wanted to represent it with more numbers, then you have a better resolution because you have more options to discretize your signal. And at some point, you might have so many options that it looks almost like the original signal, right? Normally, ADCs are a very good ADC is 2 to the 12, 4,000 options. From 0 to 5, that is not that bad. You have 5 divided by that is a resolution of 1 millivolts, more or less. A very good ADC is 16 bits. So you have 16 possibilities to represent the whole range. And that times 1,000 is 0.07, so 76 nanovolts. So microvolts, sorry, which is nothing. Super precise.
So when you say that they have register the beginning, not like the whole state, just maybe 60 for analog or like all of them represent the state of the microcontroller at one step. If you have more than number of things,
No. So in this case, you have a dedicated block for the ADC only. You have a dedicated block that reads the signal and then outputs a number. And that number, it can be a register. It can be just a string of ones and zeros that represent something that is somewhere into the memory of your microcontroller. But the ADC itself, the block, it's only one pin. And then it will have associated one register, yes. But normally, you won't even deal with that register yourself unless that you want to do things very deep level. But that input that you get, it's only with one pin, goes into, let's say, this block, ADC, and then just outputs somewhere else as a variable. Okay. So this is another representation of an analog signal, and then this is, let's say, what we call logic levels. And this is a good example of a digital signal, 5 or 0 volts. No more options there. Okay. So at the end, what we are saying, and I don't want to go too deep into that, is that the more important thing to remember here is that the microcontroller at the end has some ways to interface with the world. Those are inputs. Inputs can be in different ways. It can be inputs like in digital, that can read in digital values, zeros or ones. They can be analog in some cases if you have an analog to digital converter. It can output things. So pins can also send things to the outer world and control motors, control lights, control relays, control things. We'll have a dedicated week for that. And each of the pins of the microcontroller, we have different functions. You'll see that in electronics programming, the assignment will be to read the data sheet of a microcontroller. Secret is that no one does it, but at least you need to know a little bit where to find information. The data sheet of the microcontroller is around 500 pages. Of course, you're not going to read that in a week, but it's useful to get the schema of the data sheet a little bit to feel comfortable and say, okay, here is where it describes inputs and outputs. Here is where it describes how to access a register. Here is where it describes how to use one one crystal to have a better resolution in the clock. Here is where it describes the power and inputs. Crystals. Okay. So, what else? It's probably going to be too much. Okay, I'm gonna finish. I'm gonna talk very briefly about this. We're gonna take a break, and then we're gonna talk about the different families of the micro. I think the class is going like a little bit too hard. So I'm gonna briefly talk about this section here, and then we take a break. Okay? Now let's think how microcontrollers interact with the outer world. They only understand, let's say, it's a very silly piece of material, let's say, that can interact with the outer world just with normally input, like digital inputs. You can put a 5 or a 0, but that's it. There are many ways that you can talk to a microcontroller and tell it to do things. In these cases, we have a lot of interfaces already prepared for us, like USB or FTDI, that is what you're gonna make this week, that simplify these things and implement what we call networking protocols so that you can talk to the microcontroller and it understands what you're saying. You don't have to tell the microcontroller, whenever I send you a 5 in this pin, you're gonna do this. No. Normally, there's a protocol and that establishes different rules and different ways to talk to the microcontroller. But as everything in life, there's not only one protocol. There are many different protocols. What I'm just going to mention here is how these protocols are categorized. First category is, are we sending the information in series? So all the information in a string like this, one after the other? Or are we sending the information in parallel? Are we sending all, like, do we dedicate 8 pins to send information in parallel? And you might have seen this in some machines or all computers in the puerto paralelo, which is one port that has a lot of pins, like this one. So this is a port that accepts communications in parallel. It has a lot of pins coming in, and information is sent in waves, let's say. So at one moment of time, it sends information in all the pins, and then in all the pins, another piece of information, which is very good because you can send a lot of information per second. That's great. But then you require a lot of pins. You could talk also only having one, you could, instead of that, you could talk only having one cable and sending the information in the string in what we call series. That is normally how this works. USB stands for Universal Serial Bus, which is a serial communication protocol that sends data in a row. Okay?
And we give also like lines.
Yes, actually USB does what is called differential pair. It has 2 lines that the difference between the lines on the difference in voltage is what makes the data. So it's a little bit like smart in that way, so that if you lose something, you at least can recuperate either one of the lines. You can also have series communication with one cable, with more than one cables, but normally one cable dedicates to send the data and other cables dedicate to send, for instance, a clock. Like how fast that information is being sent so that the other end understands it. That's, for instance, what we understand for synchronous versus asynchronous communication. Am I setting the pace of the communication? Do I have to decide at which speed I'm talking? Or do I have to send a dedicated line in which I mark how fast the communication is happening? It's the same as if you were, I cannot think about a very good example. it will happen in Arduino, and you'll see this very frequently. When you open the Arduino serial port, actually, I'm gonna disappear from this camera. This Arduino, this is USB, and this will start making sense with port. Why not? It's not reading it. Let's try. Okay, well, I'm not able to read it, but in the Arduino serial monitor, you have this little drop down here that says 9,600 watts. That's the speed at which the communication is happening. And you have to specify that because your microcontroller is sending the data and it doesn't care how fast you're reading it. And if you change that to a bad value, you'll see that when you read the information that this is sending, for instance, super fast and you read it very slow, you just read garbage. You just read some communication, some parts of the communication, but you don't read the whole thing, and you're not able to analyze it. You have to somehow know that this is sending at 9,600 or 115,000 or whatever, so that you are able to read the communication that is sending. That is called asynchronous communication. It means that there's no way for the microcontroller to send at which speed I'm giving you the data. In other situations, you could be in what we call synchronous communication. Asynchronous is only one cable, we just send the data and that's it. We don't care about anything else. Normally, you will see that is called TXRX, transmission receive. And there's no, the data is sent in series, and there's no information on how fast the information is being sent. On other situations, for instance, you have another cable in which you have the data and another one that has the clock. That basically is, again, the director of the orchestra. Remember that the microcontrollers are very dumb. They don't have any concept of what time is. So there has to be always something that marks the time and keeps the pace like in the band, like this is the speed that the communication is happening, and you dedicate one cable for that. So you'll see that different communications protocols have 6 cables, 4 cables, 2 cables, 120 cables, depends. Normally you will use either USB, RxTX, which is serial and asynchronous. And you will also, in the networking week at the very end, you'll start using some protocols called I2C, SPI, etc., etc., that are, let's say, things for the future, but just that is information. Very last thing that we're going to talk about. Well, here is SPI, for instance. This is if you did Fab Academy 2-3 years ago, you would have done one ISP, so in-system programming, one of these little. Oh, sorry, I lost it. So if you had done Fab Academy some years ago, for instance, when I did it 2-3 years ago, you would have done one of these that has this header, 6 pins, which is an SPI communication, which is this header in here. This is called header. It's also here in this board. Basically, you connect it here, and instead of programming the microcontroller through USB, you program it through here. And you would have done this version. This is in-system program ISP that talks SPI. Sorry, it's not. There's a lot of acronyms, but SPI is the communication protocol that has these formats and has this shape here. Now you're gonna do something that is like this one that has 6 cables. You will do your own version for this in this week. But instead of being sold at, I think it's 16 euros the cable, one cable, 16 euros, you will make your own, and I think the chip is around 4 or 5 euros, and you will manufacture your own. This is what we call FTDI. This you will get so familiar to this that you will hate it at some point. FTDI is Future Technologies, I don't know what, international, is an acronym for that. Future Technology Devices International is the acronym of FTDI, and this is an FTDI cable. You have some of this here, but basically is a conversion between USB to this header here. This header here, it has ground, voltage, TX, and RX. So it's able to send data to the microcontroller and receive it from the microcontroller.
This one doesn't receive.
This one receives as well, yes.
And why did you do this
Because the microcontrollers that you're going to use this year, or that we started using last year, accept this protocol for communication that is a little bit easier and faster to implement. You cannot still do one of these. If you want to really go into these things, read this documentation from today. You will get there's a lot of links hidden that we didn't see. And I also recommend you to go to, in my documentation from the academy, I analyzed one of these in the electronics production week and try to understand the different things, the bootloaders things, etc. And this is the ISP. Since we make it in the Fab Lab, we call it Fab ISP. And I try to understand what the ISP, so this is the whole thing, sorry. This is the board that we used to make. We will make something different, but this is the one that replaces this. I try to understand what the different components did. You don't have to do it, but if you want, you can. And you can read what each of the functions do. Here you see that there's this header, this one here, that is used to program the microcontroller that is then going to program other microcontrollers. Okay, so here you can see the ISP when you program it first, and then when it programs other things. Why is there a USB? How do you implement USB, etc., etc. This year, then what we're gonna do is what is hidden in the head of the cable here, in this part. Oops. Here inside, there is this thing. FTDI. Sorry, let me see if I find the board. FTDI. Exactly, this one. So what this has inside is something very similar to this. USB on one side, the FTDI chip that understands USB and talks serial communication on the other side, RX, and sends it through this header. We're gonna make a version that is a little different to this. We'll see it after the break. There are two boards. One that is the first part, and then another additional board. We'll see why afterwards. But basically, it's an instrument for you to program the boards using a protocol or a chip that is able to read USB and send afterwards RX states. And that is a generic form of communication. Why do we use it? Because the microcontrollers that we're going to use in File Academy are able to understand RX, so serial communication. We could use all the microcontrollers and then they will need this header that are SPI. It's more or less, I know that this is a lot. I don't know, just if you want to slow down or something, please tell me. Otherwise, I keep going. Should we take a break for 10 minutes? Do you guys have any questions at home? Or
No,
No?
all clear.
Okay, the second part is gonna be super quick. It's not gonna be so hard. Maybe half an hour and we're done. minutes. See my screen, okay. So, sorry if the first part was a little bit too much. Just to put a little bit of perspective on the idea for this week. This is an actual FTDI cable. So you see USB. It has a small, we call it FTDI chip inside, talks USB and sends serial to the other side, okay, RX sticks. These connectors is, well, this is what you saw on my screen earlier. Let me just see that everyone at home is seeing everything. I don't know if they're there or not. What you're gonna do is this cable, this part here, with this connector attached to this in a small PCB. Just so we recap a little bit, why are we doing this? First, because you're going to learn how to produce and manufacture electronics by yourself in these milling machines. But secondly, because you're going to make a programmer for the rest of electronics of your academy. That programmer can be this, or depending on the family of microcontrollers that we have, you will use a different one, depending on what the microcontroller says. What we are going to talk about right now is I want to give you a small introduction. I don't know how this is going to work. Or maybe, wait. All the different families of microcontrollers that we have. This, for instance, is the board that you're going to manufacture. This is the same as that cable, let's say. So this board is the same as the cable there. But as you see here, I will put them on the table and then pass the camera. There are different types of programs. So this is an FPDI programmer. This is for another type of chip that goes along with this other board. It's able to program these chips. This also goes there. This also goes there. This is the same FPDI. You can start passing them. All of those are ISPs. And they are for different.
Are the same?
ISP in system programming. So for those at home, so where we're talking about this one is the same as the cable. And then different types of microcontrollers and different types of boards have different ways to program them. This is a board and this is a board. But these, for instance, are programmers. These are programmers. This is another board of that type. Another programmer, microcontrollers. So what you're gonna make this week is one of these. You can choose. Normally we recommend to do these FPDIs, but at the end of the day, if you wanted to use another microcontroller and you know which one you want to use, which you probably don't at this moment, you can do any of the other ones. What I recommend you to do is this one. Okay?
Then well, to launch, to set up programs here, we need to connect this, no?
So this one here, you already see how it connects. This goes to your computer, talks, understand the data from the computer, sends it over here, then it boards this program. Once this board is programmed, you detach it, and then this board, you either put power in some of these pins or in here, and it operates, and that's the thing.
And then if we remove this part and this part and this, make put these pieces here, we will we are directly USB.
That is, for instance, what
Arduino.
an Arduino does.
Okay.
Here, if you want to pass them as well, there are different examples of microcontrollers. And at the end of the day, you will see, and what we will demystify is the concept of what an electronic board is. That makes your life easy like this. This, in fact, is something very similar to more or less that. So this is more or less, not exactly, but around. Now, this you do it yourself. These are doing more options, of course, but this year is what we're going to learn how to do to make things better. Examples that go a little bit further. Let me see if I can find one thing that we did last year here. This board here, that is the small 6-pack machine that we designed last year for COVID. So this board here, you can detach it. Has USB, the same FTDI chip, the same as this one. The USB here is USB-A, this is micro USB-B. The rest is just to adapt power, an LED, a small battery, etc., and Wi-Fi antenna. This basically what we do is expose all the pins, input, output, things, control things. In this case, read motors or read sensors, control motors with these other boards. This is the board that we designed here and we manufactured afterwards. The idea is that by the end of the academy, you will be able to do one of these. Not with, let's say, silk screen and all this, but with one of these, which will be able to make it by yourself, and also one of these. That's whatever you want, but this is what we're going.
How do you take decisions about when for
Sorry?
How do you take decisions about which microcontroller you need to use?
Yes. Okay, that's a good question. Normally, the first, so one has to self-assess, let's say. The first question that you have to ask is how much streams do you have? How much streams do I have? Am I total noob or do I have some streams? If I'm a total noob and I don't have any streams on electronics, and I want to keep it simple and also use something that is very well documented. So for instance, what I'm going to do is reuse a microcontroller that is either in Arduino, Adafruit, or the SparkFun boards. You go to any of those and you see what is the Arduino, the chip in an Arduino Uno at Mega 256. Okay, at Mega 256 is a microcontroller that is well documented, that there are tons of examples online, that has libraries everywhere, etc. Does that suit my needs? Does it have, for instance, do I need 10 analog inputs and this only has 8? Okay, what do I do? Do I put 2 or do I go for another one? And you start the cycle again. If I ask, is there another Arduino, other fruit board, SparkFun that does this, that is well documented, that has libraries, and is well supported? Yes, then I pick that one. That's my flow of thinking. How do you know if it's well documented or not? First of all, if it's been sold. If it's been sold commercially in Adafruit, Arduino, and SparkFun, it's going to be well documented. Second thing is that you go into GitHub and you say Arduino Uno. You go there, and how many results for Arduino Uno do you have? 7,000. Then you go, for instance, you want to talk with Arduino, sorry, Adafruit. Let's imagine.
So in that case, you take a standard board and you decide to use that microcontroller according to how the board.
Exactly. That's
And
what
then
I
you
would.
can like just take the microcontroller and you say.
So for instance, I see that, imagine that I want to make a board that has a Wi-Fi antenna like this. This one here has, this is a board that you will use soon, or a microcontroller that you will use soon. It's called ESP32. It's a microcontroller that not only does things, but also has Wi-Fi and Bluetooth. It's very useful because you can talk to the internet and also use Bluetooth devices with it. This here is normally used in a board called Feather ESP32 in other words. So how do I know how to wire this thing? Okay, I go to Adafruit in GitHub and I see, Adafruit HUSA 32 ESP32. I open it and here I have the schematics and files. Let me see where they are. Board and schematic. It's they manufacture and they design, manufacture, and sell, and everything is open. Yeah. Adafruit ESP32. So you go either on GitHub. In GitHub, you have the hardware files to download just a schematic of this. You can just simply Google or DuckDuckGo it. You see here. And then some things already start sound familiar, right? So here you have on the left side, you have the antenna. Normally antennas are manufactured, not all of them, but the ones that we use very often here are called ESP, and they are manufactured by a Chinese supplier that is called Expressive. And the number after that defines the model. ESP12, ESP8266, we use the ESP32. Here already you see the wiring. You see how USB to serial communication happens between USB and the board. You even have a LiPo charger for batteries. You have the headers. You have a reset button. And here, I don't know what this is. This is power. So power input and adaptation so that it's clean for the microcontroller to work. We'll see all of this in electronics design. Why do you put all these circuits? But basically what I would do is, what needs do I have? What experience do I have? What has been done before? If I am very good in electronics, that I don't know anyone here in the house that is so good in electronics that can just do it by itself, by him or herself directly off the shelf. What I do is go and see how people with more experience than me has done it. And Adafruit, Arduino, etc. are very good examples. If I want to use something that is not documented, that the only information that I found is in weird forums, that is from 10 years ago, I never would use that chip. Why? Because I'm going to face one problem at some point that is going to be a source problem, and I'm not going to be able to do my project. And normally think about this as these microcontrollers, even if we put them in boards that are open. So this design of the board is open, the microcontroller is not open, it's proprietary. And now that's a different story with, I don't know if you've heard of RISC-V. RISC-V is let's say, an initiative to make open hardware designs from the, let's say, the very um, bottom. So everything, even the instructions in the core and the hardware itself, can be open. And you will see a new family of boards that are fully open. But now this is not open. This in here, or whatever we design, this machine or the Smart Citizen or the Raspberry Pi. The Raspberry Pi, it's an open source project. This here is a Broadcom chip that who knows what the fuck is inside? No one knows, only Broadcom, right? So if I see something that is, if I have to choose between a super closed source, not documented, only niche operations, things like this, and I don't have experience, I would never choose it. I would never design a Raspberry Pi myself because I don't know anything about this chip. Raspberry Pi has contact with Broadcom, and Broadcom tells them, you put this chip in here, you do this, and this is how it works. But I don't have the money to do that. So what do I have to do? I have to keep it simple, use a chip that they go into another level, even if they are closed source. There's already a lot of people and an old documentation and experience that is being shared that I can reuse. And that's why I would choose a chip that is not documented well or hasn't been tested by other people in the community. For me, it's a no-go.
You ever have a brother when you try like on Wi-Fi Bluetooth 2.5 ports and it tells you can use this chip?
No, there's no such thing. But what you can do is normally what manufacturers give you is these things.
Okay.
A table of, let's say, what do you want for your microcontroller to do? Let's see if I can open this image. So this is all the family from AVR, the same manufacturer that makes this chip, well, this SPI, or this chip here, okay? And this is the table of, let's say, the product table. How many inputs do you want? ADCs. Number of bits, 8. How many channels? 4, 12, 16. Then, of course, the deeper you go into the table, the more features it has, the more expensive it is. And the same you have to check in here. If you want to add Wi-Fi communication, Bluetooth, etc., you have to look off the Bluetooth communication for the AVR, ExpressIP, etc. Normally, to get your head around these things a little bit, is if I want, and this is how we normally do it. If I want Wi-Fi communication, I'm going to be on the right side of the screen. I'm going to use Expressive. Normally, is what we have been using because Adafruit has used ESP32, ESP12, ESP8266 to make Wi-Fi communication boards, and a lot of people have done it, and it's very cheap, easy to find documentation. This is what we use normally in here. There are other brands and other manufacturers that do these things, but it's like, if you want Wi-Fi, just use one of these, and it's going to work. If you don't want Wi-Fi, depends on what your project is, number of ADCs, channels, memory, what it has to do. Do you have to process sound? Do you have to process digital input signals, control motors, and I don't know. Then you go to the left side, and then mainly you have the, let's say, the god in microcontrollers is called Microchip. Company that has both AVR and ARM. AVR is normally these types of microcontrollers. ARM is microcontrollers and more complex architectures, even things that run on a Raspberry Pi or on a computer. It's like a competitor to Intel, for instance, in microprocessors. So, yeah.
ARM, so it's like the blade is designed inside, or there's like the sub layers of something made by ARM company, which is inside the microchip.
Yeah, I think the history, I'm not knowing fully, but as far as I understand, ARM was bought by Microchip at some point, and they were a Microchip designer and manufacturer, and as well same well as AVR, and they are both now part of the conglomerate of Microchip. And probably Microchip also has other people in there.
Wasn't it bought by NVIDIA?
Sorry?
Wasn't it bought by NVIDIA? Or
That I don't know. I thought it was always part from Microchip. It could that honestly, probably the part of microprocessors or GPUs was probably bought by some. Yes, I remember something like this. This recently, 1 or 2 months ago. Yeah. You're right. I don't know if it was fully ARM or part of it, but it was very recent. Either way, right now, in the lab, we are restricted, it's a lot of options, to these families of microcontrollers. Inside of each family, there's more chips, depending on memory, number of pins, etc. But first thing that you have to think that the chip has to communicate wirelessly with the outer world, yes or no? Yes. I go to the right side, ESP, something. It doesn't, okay, then I have to go to the left side, and then I choose, depending on other Fab Academy projects, the availability here, what I want to do, my experience, what is documented, etc. Inside of this page, and with this I'm going to conclude, I don't want to give you all the information here. There are instructions and documentation of how to program each of the microcontrollers. You can have a look through this when you have to program them, not now. What are even the commands that you have to put either in Arduino IDE or other terminal applications so that you can program the microcontrollers from your computer. It gives you also the information on the board that we manufacture and the equivalent in, let's say, the commercial world. So, for instance, for this family, we will use the Fab ISP, the one that I was showing earlier, and this is the ISP from Atmel that they manufacture and sell it to you for review. And for each of the families, this applies. So AVR Series 1, which is a new family. This is what you are going to do this year. Well, this is the option that we recommend you to do. The FTDI cable, but the version of the board. This is the family of AVR, the 80 Tiny Series 1 family of chips. They have different configurations between the number of pins and the flash size. How you connect it, you will see this in programming. Some more options, how to program it, the same for ARM. The other more complex chips, how you connect it, how you program it, etc. So some instructions. For this today, we're not going to see it. We'll end up here. We'll revisit this in 2 weeks once you have your boards ready. Okay. Yeah. FTDI.
I mean the design of the project, the labs and everything.
Yeah.
This we have to design it ourselves.
No, you already have it. If you go to the Academy page, Academy. Content 2021 schedule, electronics production. Here you have Neil's class from yesterday. In-circuit programmer. And here you have all the files. UPDI, you have here the board itself, the components, the traces, which is the PNG file that you send to the machine. How it looks, the schematics, let's say. And then we'll see these, but Neil, when he designs, he does it with scripting. It doesn't use an interface. So this is the definition of the board. Don't worry about the first one. I've never used it. But these are the different options. Okay. This PNG, basically, you send it to modules or mods, which converts this into instruction for the machine. Sorry, the machine will build the board. Since you weren't here yesterday, we'll walk you through the process afterwards so that you can manufacture. But basically, the idea is that when we design, we output, let's say, this image. This image is how the board is going to look from the top. Let's take this example. You see here, the white part is the copper. So basically, it's like the screen, like the seal screen or the screening for the machine to remove the copper. Now the machine cannot read PNGs and transform them into motor instructions, but there's a program that the FAO Academy maintains that is called FAO modules. Probably you also saw this one called mods that I don't even, I don't use this one, but this is the one that they recommend lately. This one, did you see this yesterday with Yusef? Mods? Yeah, okay. I never used this, you're free to choose. There's another version that is the old version that is called FAT modules. That's the one I use. I like it a little bit better, but it's probably because it's the one that I learned with. You can use either of them, okay? I'm gonna just show the workflow here. You input the PNG file. For instance, this is a board that I had in my computer. This is the board that I want to manufacture. It has to be a high resolution image, 1000 dpi at least, or 900 dpi at least, in black and white. What this program is going to do is find the areas where there is an edge between black and white, and in there it's going to put the tool. It's going to say remove copper there. Okay, so here we want first to invert it because the tool is going to be on the black side of the image, and we want these little pads in black to be copper. So if I left it like this, it's going to eliminate only the black parts. So I invert it, and now the program what it's going to calculate is the instructions with a certain type of parameters like diameter, size, speed, etc. If you press on calculate, you'll see what I'm talking about, which is these are the toolpaths. That is then a text file that we send it to the machine and makes the PCB for us. Okay, that's the whole thing for this week. The designs for the boards are already done. If you want, you can make your own. There's no problem for that, but we haven't shown you how to design boards, so probably that's going to be difficult. This week is just to learn how to manufacture the board and solder it, which is not going to be easy either. Okay. At the end, the test for this board is that when we put it into the USB port, your computer doesn't explode, and then it recognizes it. So there should be something like FTDI chip detected or something like that. Okay. First of all, of course, I don't know if you saw it yesterday, but you wouldn't connect it first, the first time. You use a multimeter and you check that there are no shorts, that there are no problems in the board, and then you connect it. And even you don't connect it directly, you connect it with a USB extension cable. Because if you connect it and something happens in here, goodbye USB ports. If you connect it to a USB cable, if you burn the USB cable, it's fine. But you don't burn the USB. Okay. There are some USB cables there. If not, it's not a bad idea to have your own. It's €2 in a shop. It's just a extension cable. Is that clear in terms of what you have to do for the week?
There was a question on the chat that I also wanted to ask.
Sorry.
Like the difference between the three lines that we have in the
Yes. So the way that we program this the UPDI is used for what we call AVR Series 1 microcontrollers. Okay, they have a way to program them that is a little bit special. That is called UPDI. That is a new protocol that AVR has designed that only uses one pin. In other situations, we use 6. This is very convenient because only uses 1. What do you have to do for that? In an FTDI converter, the same one as this one, USB to serial, USB to 6 cables, but basically you just care about ground, voltage, RX, and TX, just 4 of them. If you join TX and RX, which are the ones that the data is going through, with a 4 kilo ohms, 4.7, 5 kilo ohms resistor, if you join them with a resistor in between, then that you can send as UPDI into the microcontroller. And the microcontroller magically understands that. Okay? That, no? So this cable, imagine that you took the yellow and the orange ones and you put a resistor, a 5 kilo ohm resistors between them. You take just one cable out and you put it into the microcontroller. You send data here and the microcontroller gets programmed. That doesn't normally happen, but it's the new protocol that they designed. Now, depending on where you stop, you have different options. Option 1, FTDI, and then a little board with the resistor, the 5 kilo ohm resistor. One board, another board. Second option, this board with the FTDI and the resistor in it. That's the 2 boards. In this case, here, that's why there are 3 boards. 3 boards there, come on. Oh, here, okay. That's why there are 3 boards, but there are actually, well, actually there are 3 options. Option 3, everything in the same board. Cable and resistor all together, one cable out. You have a header that has 2 pins, ground and 1 cable, UPDI. Second option, you split this board in 2, and you have one equivalent to the cable and one that has just the resistor, 6 pins in, 2 pins out, and 1 resistor joining 2 of the places. Third option is that you use the cable, that we don't let you do it for this week, and that you have the other tiny board, and you just put the other board here, and use it to program. You will be able to do that once you have shown that you're able to make the FTDI cable, the FTDI version, so the complex board. Because this tiny board is at 1 resistor, come on. That's not that much to solder, it takes 5 minutes to make. So you have to make either this is the cable, this is the resistor, or either this, which has the resistor already in the same board. And that's it. Yeah.
The microchip, they all accept either both protocols, or it's one or another?
To program them, well, the protocol is the same. So there's only one protocol that they accept. This family, manufactured by AVR, called Series 1, AVR Series 1, they accept UPDI, which only uses 1 pin. You could program it as well with this FTDI directly. You could, but it's not the normal standard, let's say. Now they implemented that so that you don't have to use FTDI. You're going to use this plus a small resistor between the 2 lines. You could actually, if you wanted, just take ground, take the 2 lines, put a resistor badly, like with duct tape, if you wanted, take 1 cable and program it. That would potentially work. But the idea is that you manufacture a program. Okay? So the 3 options, is this answering the question? Yeah. So those are the 3 options. Why do we, you might be wondering, why do you do this stupid thing where you split the boards into two here, and you can put the resistor already always in this one, and you just have 2 pins, and that's it. Well, because this is also already an FTDI cable, and FTDI cables are used also for many other things. They can be used for talking to many microcontrollers, boards like this that are for CNC, etc. So FTDI is a very common standard. It's like USB or HDMI or these things. UPDI is very niche. So if you design a board that only talks to UPDI, you're wasting silicon. So into making just one board that doesn't support FTDI too, when you are just one step away to do it. Does that make sense? Or not? Yeah. I recommend you to make it too. I actually recommend you to do this one first, the small one. You make a small board, you get a little bit of practice. If you fuck it up, it's not gonna be a big deal because it's a small board. It will take little time to make it again. Only has one resistor. There's no big deal in that. And then you make this other one. But it's up to you. If you want to go with the big one or both of them at the same time, you decide that. We don't say. One advice, and with this I finish, is that I like projects that normally tend to atomize and make smaller boards than one super big board. Why do I say that? Because your board is going to burn and it's going to fail at some moment. And when you're in June and you want to make your final project and you have to make one board that is like this, two-sided with 3 microcontrollers, 10 pins, and whatever, you have to mill that. It's 2 hours to mill, 6 hours to solder. If you make one board that only has one tiny thing in it, even if it's more boards, but you learn how to connect them, when that board fails, you have 5 minutes to mill another one, 5 minutes to solder a new one. If you make the big board and it fails the big one, 1 day is wasted. So that's one advice. So that's why also there's this option. It's easier to solve any problem here. Think about this board as well, something that you're going to plug and unplug many times, many times, because you're going to program 10 million times in the academy. It's going to get bad connections, etc. Milling this board is 5 minutes. No complication for that. Okay.
I have a question more on the kind of like logistics practical side in the future of the Top Academy. So
Okay.
let's say that we are considering kind of like different processors or like different modules. We want to use, for example, Wi-Fi, but we haven't used any before, and we wanna try.
Yeah.
So would it be okay for the sake of time to try with a commercial solution and later on like build our own board when we know what we are using?
Sure, yeah. You have to see this as an iterative development.
Yeah.
And at the end of the day, what you have to show is that you know how to make your own electronics. How you get there, I don't care. But you have to iterate. If you want to iterate directly making your own, that's fine. But if you want to iterate by using a commercial one and then using your own, that's also good. For me, there's no problem. But in each week, I say that, but I also say that if you map more or less what your development is going to be through the assignments, you should have enough iterations to be able to do that with your own electronics and never use a commercial one. But it's up to you how you want to use it. If you imagine you wanted to start doing all the academy with an FTDI cable and never do a programmer, for me, conceptually that's okay. But at the end of the day, you didn't show that you are able to do your own programming, and you will have to do it at the end. It's up to you.
Yeah.
I wouldn't recommend that, especially in these initial weeks. After that, if you want to iterate faster, it's fine.
No, I'm not talking about the assignment at all. Like, of course, like we need to do a programmer. Like, going to do a programmer. I'm thinking on like if I wanna try 3 or 4 different modules, if I need to build them before choosing which one.
Yeah, that's perfectly fine.
Forever.
No, of course, that's perfectly fine. And one of the steps that she was asking earlier, that how do you choose the microcontroller? you would have to choose not only based on your experience, but if you have the possibility to test them because they are here, of course, use them. Yeah. I mean, it will make you be familiar with the board, and it's also like a good example to say, okay, I see the schematic there. I have the board physically. I know that this board works. If I try to reproduce something similar to this, it's going to work.
Yeah.
So of course, that's, I mean, at the end of the day, think of this, that you want to develop a working methodology more than a skill set that is very broad and thick, let's say. What I'm trying to say is that if you learn how to iterate, and by iterating, you have to pass through commercial solutions for that, so that you can make your own version afterwards, that is a working methodology that is perfectly valid, and that is what I do. So, of course.
And we have things to try here.
Yes, 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 of course. There's Arduinos, there's ESP32s, there's many, many, many. Of course.
We could do, let's say, the other way, that for your final project to include, say, an Arduino just in order to make it work, and then you complete with the assignments.
Yeah, the only thing is, yeah, but the only thing is that the final project, it has to fulfill 3 requirements. Is that you have an additive, subtractive methods, and that not only input and output, but also that the electronics are used. You could make a hat. For instance, you could make something that go on top of this, that has electronics in it, that you designed, and that at least if you put something on it, there has to be a microcontroller. It cannot be something passive. There has to be some microcontroller in there, even if it's very simple, and this one takes care of everything, but there has to be one, and you have to design it. Yeah. And that is
commercial one, you have to add one that you design the system.
Yeah, exactly. Yeah. At least there has to be one in a board that you have designed. And that board needs to have not only that microcontroller program, but also inputs and outputs. That's the, let's say, the requirement. If you want to go full-fledged and just do one board that you design and that does everything, perfect. If you want to do this other option, that's also good, but remember the restriction of a microcontroller that you put in there. By the time you get to the end of academy, you will know how to do Arduinos. So probably you will be eager to make your own, but depends. Now you probably see it like a very big thing, but it's not. It's not. Good. Any more questions? Anyone on?
If, for example, you want to use a microcontroller that probably is more, that has more, I don't know if this is the word, but has more power than what you really need. How can you know that?
How can I know that?
Yeah, but how can you go like the cheapest way possible? I don't know. I'm thinking about, for example, I want to make a PC microcontroller from Arduino, which has a lot of things that I'm not going to use. So I'm not sure if I should be choosing that or something.
Yeah.
So how do you know if you're not over-engineering?
See, if you're not over making the electronics, well, first we are here. We can support you on that. But second, I think this will come with time. It will come with experience, and you will. My recommendation, and that's probably how the Academy is done this way, is that normally you will start with very small microcontrollers, and you will see the limitation of that. Once you suffer and you see limitations in pins and memory, then you will be, okay, I'm going to increase a little bit. But now I know what I missed. If you start with a very big one from the beginning, then you never know what you need. So probably putting yourself in the situation of not having enough resources with a small microcontroller at the beginning just to try and see what happens is better and will give you more experience than going to the other side. I'm not going to be able to give you a solution for that. It will come with experience. And for me, if I had to make a project like an actual project that is going to be manufactured and everything, that will take a lot of time. And I won't probably take the decision. I will consult it with people, etc. In your case, iterate and started little and then grow. Anyone else? I see some here. Crystal oscillator. Which board do we need to make of those trees? Okay, guys, can you share here the link of this part of the page? Okay. Good. Any more questions?
About the PCB design, where we can find it.
The PCB designs, you go into the Fab Academy week. I'll put this on the.
Yeah. Okay.
So, common rule, if you go here, then the assignment, it normally has the link in there.
Yeah.
I just put it in there, and then you can find. Normally, the files that you want to manufacture are traces. Traces is the actual traces that you remove copper. Interior is the outline that cuts the PCB from the stock. So you have a copper board that is like this, and you just want to extract this. First, you do the traces, so the copper removal, and then you cut this. This is interior. It's a little confusing. Interior and traces. Okay. And of course, you do the interior first, because if you cut first, then the thing moves, and then it's impossible to make something natural. Right? More questions? No?
How do we start?
Get a board, open mods, make your files, go to the room, get some copper, put it on the machine, like stuck it to the machine, send the script to the machine, press play, and wait for the minute.
And the board, so we take the square and then it cuts into the percent.
Exactly. Yeah. You have to show that it does. So you have to not only take so for this week you have to take the PNG and then make the traces and the interior for both on separate files. They are with different tools. I'm repeating this because you didn't come yesterday. If the tool that goes for the interior is a 1/64 of an inch. It's a very small tool that is only able to scratch some the enemy, yes. The exterior, let's say the one that cuts through. So here you're only scratching the surface. You're just removing the copper layer before the epoxy resin. The other one that's around it is 1/34, 1/32 of an inch. Okay, that is a little bit bigger, a little bit more robust. You have the end mills over there in those little buckets, but ask either Giuseppe or Edu, because they have it more under control, and they will give you the end mills. I probably you will have your end mills already for the academy, let's say. So you already gave it. Okay, that's perfect. So if you already have them, then make the file, take the copper, put the end mill in. I'll walk you through the process. You put the end mill in, you tighten it, make the zero, prepare everything, then launch the file, change the tool, the other file, take the board, clean it, solder it, and take a picture. That's the whole process.
All the components.
The components are all over there in this inventory. This is a very good moment to talk about this. Inventory.fablabcm.org. Please go in it. I'll give you the password. There's an student account with a very simple password. Whenever you take components from the boxes, please write them in the inventory. Wait, this is my KeePass manager. Inventory. Student. FabLab. Okay. So I put this in an email, but this is the view that I see. But you go here, student, FabLab 001. you go to stock, which is the parts that are in there. And here you can search all the parts that we have. If you want to take a resistor, you can just search on this box here. Just put res for resistor, and you see all the values that you have. Imagine that you want to take three 4.7 kilo ohm resistors, so you go here, and you say remove stock. You take 3. Confirm, you put a note like academy assignment, submit. Okay. For every component that you take, please do this. It doesn't have to be, you will find that the interface has other ways to interact with it. Doesn't have to be one by one. You can select several from here, like that, for instance. You select them, and then can you do this? Oh, no. I'll have to have a look at that. I thought you could do it. Let me see. I'll have a look at this. You can always go, let me see, in electronics. Okay, here. If you go to electronics, you should be able to do it. So here you select, for instance, an mega, an accelerometer, and I don't know, battery connector. Click in here, count the stock, and you remove the units that you want. Or here, sorry, remove stock. You say, I take 2 accelerometers, 1 mega, 1 battery connector. You put our academy assignment, confirm, submit. And that way it helps us keep track of the stock, and we don't have to count it every year, which believe me is not nice to count components. Inventory fablabdc.com, but I share it with you. I put it in an email. Actually, I'll tell Edu to send you an email with the data for that, but I will put it also in the chat now. Chat here. User, student, password, fablab 001.
Sorry, inventory fablab?
Ahí tienes, you have it in the chat.
If we borrow, for example, a module or something, do we need to write anywhere?
If you borrow something else that is not in the inventory there,
Yeah.
that is not like consumable, like resistors and things like this, we keep internally track of these things.
Yeah.
So you have to tell us, and we write it down, let's say ourselves. And then we say, we borrow, we lend 1 Raspberry Pi to whomever. Okay?
So the best way would be like
Just-
matter note
Or tell us, but normally we're going to be here. So you just tell us, and then we just write that down. Okay. Yes.
The username is our email?
No, a student. Student. No. Students.
Inventory fablab. The name is like fablab.
It is. Okay. So anyway, just try to make sure that when you take anything from there, we'll improve those boxes also with time, so that they are a little bit easier to find at the beginning. It's a little bit difficult, but then write down eventually, because it will be really helpful for us to not have to count them every year, and then make the purchases a little bit. Yeah. And, access for inventors, students, username. and FabLab 001, all lowercase. You see here that there's something in the inventory. There's the Fab Academy inventory in which you have permission to take parts, but there's also other inventories in the house. For instance, the Smart Citizen, the emails that Miguel has for projects and these things. They are not there. You can see them, but you cannot edit them. If you need any of those components, you can ask us, but they are not there to tell you, or you don't have permission to take them, not because there's any bad thing about it, but because we just put them down so that you can see them as well. And maybe if you're looking for a component, you can think, oh, they have something in Smart Citizen that I can use. Maybe I can ask them and I will take it. But it's also internal stock for the projects that we like, I mean, are necessary for the rest. But if you need one of them or even serve as an inspiration, you can have a look what we have in the other projects and then maybe get some more references or things like that. More
Question
yeah.
about the group assignment, because it says characterize design rules for your PCB production process. What does exactly mean?
Yes, normally in the, let me go back. Trace with here is, if you go in the assignment page, sorry, in the electronics production page, put the link down here, you see that there is this board that looks like this, which basically is a stress test for the machine. These are very tiny lines on this side and a little bit wider. What you're doing is, by groups, you will launch this file in the machine and see where it's not able to reproduce the lines. So the idea is that you have very small traces, and that gives you a test for you to know which is the minimum trace that the machine can reproduce, but in both sides. So minimal trace width and minimal trace separation.
That yesterday when you showed it the tool, so to make the difference, going more or less deeper, and that's why.
No, the tool always goes on the same height, or the same depth. Sorry, and the thing is that the tool is so tiny that it's able to. In this one, it's not going to be able to go. In this one, we'll just go once, and in this one goes 2 times or 2.5 times. So the tool goes like this, and then like this, and then like this, maybe with some overlap, maybe here and here and here. But it's the idea is that you are able to, but it always goes at the same depth, that's for sure. And the machine it doesn't have the possibility to go like this. It has it, but it's not for the electronics.
But then I don't understand why sometimes it doesn't go, because or it's just the computer when it makes the program.
It does the computer when it makes the program. Yeah.
So you can do it without machining it.
No, because on this side, for instance, in this here, what you are going to test as well is how thin the trace can be, and if it moves, for instance, once, because at the end is copper attached to an epoxy resin. If the trace doesn't have enough shear adhesion, then it's not going to be attached, let's say, and it's going to move and it's going to break. So how small your trace can be is a good parameter to know from your machine. In here, very likely it won't go. At some point it might go. Well, it will go at some point, but also if you think about the machine, and you will see this with Edu, very into depth, you know that the tool is like this, if we look it from the top, and it's rotating like this. It's not the same to cut material like this than like this. It's not the same to cut material, what we call climb, which basically the material is being, so you are climbing on the material, and you are compressing the material against itself and then expelling it on the other part, or what we call conventional, which is you are cutting on the back and then spitting it on this other direction. So the material is going like this, right? That has different finishes on the quality of the milling. Normally, if you want to do very small, tiny millings, you use conventional. If you want to use things faster, you use climb. But you will see this with Edu in CNC machining, in the big one. In this case, you will see that when the tool can only go once, because it's the exact same diameter of the tool, then you'll see that one side looks good and the other one doesn't, because the material is sent in different directions. Yeah. Also, you'll see that when you have one pass, for instance, very tiny vibrations affect the finish of the quality of the machine. If you have a little bit more, then here maybe the tool is able to go twice. So you have one that probably vibrates and the next one just cleans it. Yeah. Good. So this is the group assignment that is basically characterizing your machine. If you wanted, you could make another one. This is already a demo that you can just download and test it. The purpose of here is not to make the test, but is to see how the machine behaves as well.
So then we should write like which are the best settings from here.
Exactly. Yeah, exactly. Also, well, you have to analyze this. You have to see what we talked about a little bit here. What is the minimum trace? What's the maximum? Maybe try to think a little bit what happened in some areas that it didn't look good. Maybe also you will use some of these other tiny machines. Maybe it's good to have a comparison so that some of you do the test in these ones, some of you do it on the other ones. Then you compare, take a picture of all together, and you make an assessment. These type of things are good because it brings knowledge to the lab as well and characterizes the machine, right? Yeah. Anything else? Should we call it for today? Is your brain still there? Okay. Well, thank you. We will see you around here. Little by little, we're gonna see each other more. I don't know if you like that or not, but sorry, that's the way it is. Now that this is the first week of electronics, it only gets more interesting. It will get nicer. Okay. Thank you. Thank you, everyone.
Gracias, Oscar, muchas gracias.
Have a nice day. Bye-bye.